Dear students, good morning and welcome to the lecture series on EC402 Nanoelectronics of Kerala Technological University, Kerala. The last class we have discussed about the nanomaterials and its use for fabricating different kinds of devices. Today we are going to discuss some of these devices which are fabricated with 3 to 5 semiconductor materials. The first such device used in electronics is the modulation doped field effect transistor. Before we discuss about modulation doped field effect transistor, we have to know about what are modulation doping and why is it done in materials. So what is meant by modulation doping? We know that the properties of semiconductor can be changed by doping. Doping is the process of adding impurities to the semiconductor materials in order to make its conduction fast. By adding impurities to the material, that incorporates donors and acceptors. When the doping atoms release their surplus charges, ionized donors or acceptors are left behind and act as Coulomb scatterers in the material structure, which inhibits the motion of the charges. What is the solution for this problem? The solution is to separate the active region of the device from the doping atoms, and this process is known as the modulation doping. So the modulation doping is the process of separating the active region of the device from the doping atoms. Modulation doping causes very high mobility of electrons in the device. Now we will see what are the constructional features of Modfets, how Modfets are fabricated, and what are its characteristic features and operational characteristics, how this device is operated. Modfets are devices based on the modulation doped quantum heterostructures. You know what is a heterostructure? Heterostructures are actually the junctions formed by different band gap materials. Such structures are called heterostructures. The heterostructures forms a 2D triangular quantum wells, which helps to make the electron transport very fast under the action of a bias voltage applied at the gate. Modfets are fast acting device and can be operated at very high frequencies, and hence these devices are sometimes called high electron mobility transistor, HEMT. Now we will see the structure of a Modfet. The most common heterojunctions used for the fabrication of Modfets are aluminium gallium arsenide, aluminium gallium arsenide, indium gallium arsenide, or indium aluminium arsenide, indium gallium arsenide heterointerface. Here the figure shows how the Modfets are fabricated. So here we are having a substrate which is a semi-insulated intrinsic gallium arsenide, over which all the other layers are fabricated. We will come across all these layers one by one. Okay. Here the figure We have aluminum gallium arsenide heterojunction Modfet. Here, the aluminum gallium arsenide is the wide band gap semiconductor, whereas the gallium arsenide is the narrow band gap semiconductor. The barrier layer aluminum gallium arsenide under the gate is doped, that is an n-type doped one, which is having a thickness of almost 30 nanometers, and that is except for a narrow region D0. Here this D0, that is the thickness of the spacer. We will come across what is spacer, and this is the thickness of the n-type aluminum gallium arsenide material. That is the barrier layer, and the gallium arsenide, undoped gallium arsenide material or layer is called channel layer, and that is made up of intrinsic semiconductor having no doping. It is an undoped gallium arsenide material. The heterojunctions are grown over a semi-insulating gallium arsenide substrate, what we have seen here, semi-insulating gallium arsenide, and that is done through molecular beam epitaxy or chemical vapor deposition methods. An undoped aluminum gallium arsenide spacer of thickness B0, that is approximately 50 Armstrong unit thickness, is placed between the aluminum gallium arsenide barrier layer and gallium arsenide channel layer. That is what we have seen here. So this is D0 and this is the spacer, and the spacer is actually in between the n-type aluminum gallium arsenide and the channel layer undoped gallium arsenide. This is the D0. The role of the aluminum gallium arsenide spacer is to further separate the conducting electron channel from the n-type aluminum gallium arsenide layer that generates the carriers, thus leading to the higher electron mobilities due to reduced interaction with the ionized donors. We have already seen that modulation doping is the process of separating the active region of the device from the doping atoms. So that is taking place here with the help of this aluminum gallium arsenide spacer. The top layer of heavily doped N gallium arsenide is for the source and drain ohmic contacts as shown in the schematic diagram. That is here. This is the ohmic contact for the source, and this heavily doped N-type material is for, or that is giving connections with the drain, and these are given connection with metallic contacts. The gate is also having metallic connections given here. That is for the connections to the external circuits. Okay. The metallic contacts are provided for source, drain and gate terminals. With the principle of modulation doping, carriers from the doped barrier layers are transferred to reside at the heterointerface and are away from the doped region to avoid impurity scattering. That is the function of the spacer, which avoids the carriers from not to take place in impurity scattering. And here the energy band diagram for the Modfet under off condition. This is the energy band diagram for the Modfet just under the conduction state. We will explain these one by one. Now referring to the energy band diagram, initially the material is neutral and the conduction band is flat in the aluminum gallium arsenide and in the gallium arsenide as shown in figure A. So this is figure A. Here this is the conduction band, which is flat in both, and here the EF, the Fermi level, is same throughout from the metallic side and the gallium arsenide side. When the electrons of the donors in the aluminum gallium arsenide are released, they move around and some of them diffuse into the gallium arsenide, where they lose their potential energy and are trapped in the gallium arsenide because they cannot overcome the barrier delta EC, that is the conduction band discontinuity of the structure here. So I will tell you, this is the conduction band discontinuity. So this electron from here, this from the aluminum gallium arsenide, has to pass through the D0, that is the spacer thickness, and which is through this electrons, which has to cross over this barrier due to the conduction band discontinuity too. The negatively charged electrons are now separated from the positively charged donors, which leads to the production of an electric field which drives the electron back towards the interface. The electrons are trapped in a field-induced triangular well with a typical width of 10 nanometer as shown in the figure. When this device is given with a gate voltage, then the device will just starts to conduct in order to form an electron sheet, charge sheet between the source and drain. At that particular condition, this particular device will have the conduction band at the interface. There is a production of two-dimensional electron gas. Almost the shape of this one is in the form of a triangle. That's why this is called a two-dimensional triangular well. So a two-dimensional electron gas is formed, and this electron gas that is free to move in two dimensions, but which is tightly confined in the third. That's why it is called a two-dimensional device. So it's a two-dimensional device, semiconductor device, and also this system is called a two-dimensional electron gas system or two-dimensional electron gas semiconductor material. This particular device is called. These transistors are based on the modulation doped heterojunctions, and their operation is controlled by an electric field that controls the motion of electrons along the channel, and hence the name Modfet. How this device is called Modfet is mainly due to this fact, that is, the device conductivity or the motion of electrons can be controlled, or the electron charge sheet, the motion of electrons, the electron charge sheet can be controlled with the electric field applied through the gate. This controls the electron motion along the channel. That is why it is called a Modfet. Now we will discuss about this energy band diagram for the operation of this device. The operation. How this device is operated. Modfet is properly biased with necessary voltages for its operation. So first we have to connect this device with proper biasing voltages both in the gate source and also the source to drain voltages. An electron current is created from source to drain when a voltage VDS is applied between them. This current can be modulated with a voltage signal Vg applied to the gate. In Modfets, the wideband energy gap material, that is aluminum gallium arsenide, which has got a band gap energy of 2 electron volt, and which is doped and carriers diffuse to the undoped narrow band gap material gallium arsenide. Here the gallium arsenide is the undoped narrow band material which has got an energy gap of 1.41 electron volt. So these two materials are having different energy bandwidth. band gap. The conduction channels are formed at the interface of the heterojunctions. Two-dimensional triangular quantum wells, which is almost having a thickness of 8 to 10 nanometers approximately, which are formed resulting in quantified energy levels corresponding to the direction perpendicular to the interface. These free electrons move parallel to the interface and its mobility is very high since the electrons which originate in the aluminum gallium arsenide layers are transferred to the undoped gallium arsenide layer where no impurity scattering is taking place, or whatever is the electrons which is transferred from this aluminum gallium arsenide is almost available at the gallium arsenide because there is no impurity scattering takes place in the device due to the introduction of the spacers and all that we have seen. So there is no impurity scattering takes place when they move under the action of an electric field parallel to the interface. Now we will see what are all the conditions which governs the operation of this device. Under equilibrium condition, that is when the gate voltage is not applied, it means that gate voltage is 0 volt. The Fermi level EF is the same throughout the device. The channel conductance is very low. It means that the impedance of the device is very high at the time when no gate voltage is applied, or the device is not operating, or the device is in the off condition under this situation. Now, if we gradually increase the gate voltage, if Vg is greater than a voltage Vt, that is the threshold voltage for conduction. Now the conduction and valence band are tilted and the electrons in the aluminum gallium arsenide accumulate at the hetero interface, forming a two-dimensional electron gas inside the triangular well. That is, if Vg is greater than the threshold voltage. Now here this conduction band, that is the valence band, this is the band diagram. Here the conduction band is now tilted like this, and the bottom side of this conduction band is coinciding with the Fermi level, where there is a channel created, electron channel created. That is essentially a two-dimensional electron gas, which is almost in the form of a triangle. That is why it is called a two-dimensional triangular potential well. Where Vg and Vt are the gate voltage and threshold voltage. At this particular condition of formation of conducting channel at the interface, the channel conductance is very high, or an electron sheet is created between source and drain due to the application of gate voltage. This way, a controlled switching of the conductance of the channel is achieved. Q5Bn is the barrier height of the metal on the wide band gap semiconductor. That is here. Q5Bn, this is the barrier for the metal of the aluminum gallium arsenide side. Delta EC is the conduction band discontinuity for the heterojunction structure, and Vp is the pinch off voltage, which is given by the equation Vp is equal to Q by epsilon S0 to d n dx dx. That is equal to Q nd d1 square divided by 2 epsilon s, where nd is the doping constant for the n-type aluminum gallium arsenide, d1 is the thickness of the aluminum gallium arsenide material, epsilon s is the dielectric permittivity of the spacer. A key parameter for the operation of a Modfet is the threshold voltage VT that we have already seen, and which is the gate bias at which the electron channel starts to form between the source and drain. The threshold voltage VT corresponds to the situation when the bottom of the conduction band at the gallium arsenide surface coincides with the Fermi level, and that is given by Vt is equal to 5Bn minus delta Ec divided by Q minus the pinch off voltage Vp. The threshold voltage Vt can be adjusted by using different values for 5Bn and Vp. Delta Ec is fixed for a given set of semiconductors. So we can adjust Vt with the help of changing the values of 5Bn and Vp. When the gate voltage is larger than Vt, an electron charge sheet is capacitively induced by the gate at the heterojunction interface. This charge sheet is also called the two-dimensional electron gas, that is 2D electron gas. The expression for the saturation current IDS is dependent on the gate voltage given by the drain current saturation ID set is almost equal to, approximately equal to Vg minus Vt the whole square. This means that the IV characteristic of Modfet is very similar to that of MOSFET, metal oxide silicon field effect transistor, that we have already learned. Modfet is a low noise device having very good frequency response characteristics. Modfets are preferred in signal amplification in the microwave range up to frequencies of 300 GHz. That is about 6 times higher than the maximum operation frequency of transistors fabricated with MOS technology. So that is the main advantage of using Modfets, especially in integrated systems, integrated circuits. Now we will see what are the applications of Modfets. As we have seen, Modfets are devices which can operate at a very high frequencies of the order of 60 GHz or more, and that can be used for high speed applications. The device has a very good transconductance, having very low noise figure, and hence can be used for low noise signal amplifiers. Since this device has got a very low noise figure, so due to its noise performance, Modfets are used in power amplifiers, oscillators, mixers operating at a frequency of the order of 100 GHz. These devices are used in wide range of RF design applications, including cellular communication, that is in our mobile phones, direct broadcast receivers DBS, radar, radio astronomy, and any RF applications that require low noise, high frequency performance. With this, we conclude this session on Modfets. I hope you have understood this device very well, and if you have any doubt, you can ask me and you can just inform me over mails. Okay, thank you.